Hello. In this chapter, we will be discussing nuclear magnetic resonance spectroscopy. This is the second chapter where we discuss spectroscopic techniques for identification of organic molecules. By the end of the chapter, we will be able to describe the interaction between the EM radiation and atomic nuclei in a magnetic field that makes NMR spectroscopy possible. We will explain how NMR spectrometers work and describe the process of preparing a sample for NMR spectral analysis. We'll be able to tell the significance of the number of signals along with their locations, areas, and shapes in an NMR spectrum. We'll be able to explain the chemical equivalence and a process for identifying whether two protons are homotopic, enantiotopic, or not chemically equivalent. We will learn terms such as chemical shift, inductive effect, anisotropic effect, and describe the signals produced by methyl, methylene, and methine groups. We will define the term integration in the context of NMR and explain what it indicates. We will be able to tell what is multiplicity and explain what happens during a spin-spin splitting. We will be able to draw an expected proton NMR spectrum of a compound, distinguish between compounds using proton NMR spectroscopy, explain the process for analysis of a proton NMR spectrum, explain the importance of averaging and broadband decoupling in a carbon-13 NMR spectroscopy, explain the significance of the number of signals in a carbon NMR spectrum, and describe what information the EPT carbon NMR spectroscopy can provide. As an introduction, nuclear magnetic resonance, or NMR, spectroscopy may be the most powerful technique of gaining structural information about organic compounds. This is the favorite technique for organic chemists. NMR involves an interaction between an electromagnetic radiation and the nucleus of an atom. We will focus on carbon and proton nuclei for analysis of organic compounds for obvious reasons. The structure of a molecule affects how the radiation interacts with each nucleus in the molecule. We will see that throughout this chapter. Protons and neutrons in a nucleus behave as if they are spinning. If an atom has an odd number of protons and or neutrons, it will have a net nuclear spin. Some of these include proton or hydrogen, carbon, nitrogen, fluorine, and phosphorus. The spinning charge in the nucleus creates what we call a magnetic moment. If you have a magnetic moment, you have a magnetic field. Remember that when you have an electric field somewhere perpendicular to that electric field, you're going to have a magnetic field. So what that means is that here is my nucleus. The rotation goes this way from left to right in the image here. So perpendicular to that, you're going to have a magnetic field. So these are the magnetic lines of force associated with that rotation, right? That's why we have electromagnetics. So every time you have an electric field, you have a magnetic field perpendicular to it. We take advantage of that magnetic moment. That's the basis for NMR spectroscopy. If the normally disordered magnetic moments of atoms, right, they're just moving around everywhere, if they're exposed to an external magnetic field, and we use the term B sub 0 for external magnetic field, their magnetic moments will align with the field or against the field. So you got a bunch of nuclei just randomly moving around, you expose them to a very strong magnetic field, then all of these are going to move into straight lines. They're going to be either parallel or anti-parallel to that field that you're applying. That's what this image means. So your alpha are going to be with the magnetic field, and your beta are going to be against that magnetic field that you're applying. Beta spin state, that's what we're going to call when you have opposing magnetic fields. They're higher energy spin state. They're sort of aligned against that gradient, so that you should expect them to have a higher energy. And then you have the alpha spin state. They're aligned with the magnetic field, and we associate those with lower energy spin states. The difference between your beta and your alpha state, we're going to call that the delta E, or the energy gap. When an atom with an alpha spin state is exposed to radio waves with just the right energy, right, just enough that it matches the delta E right here, the photons are absorbed and the spin flips to the beta state. So you want to add just enough energy for this alpha spin state to jump to the beta spin state. The stronger the magnetic field, the greater that energy gap. So this number is not going to be the same across every single nuclei. It actually varies, and it depends on not just on the nuclei, but in its environment. So this is going to be very unique, and the stronger that delta E, the greater that energy gap. So that applied magnetic field causes electrons to circulate, inducing an opposing magnetic field. We call that diamagnetism, which is different from paramagnetism, which is in favor of the magnetic field. Nuclei then experience a smaller applied magnetic field and are said to be shielded, requiring less energy for that spin flip that we just mentioned. Nuclei surrounded by less electron density are said to be de-shielded, so that would be the opposite of what we just said. The amount of radio wave energy necessary for that alpha to beta energy transition depends on the electronic environment for the atom. When the alpha spins are flipped to beta spins, energy is absorbed and the atoms are said to be in resonance. We use the term resonance here, and it's going to mean something completely different to the resonance we saw from benzene and all these different things that we've seen so far. We're talking about the alpha to beta flip, right? That's that change. That's what we call to be in resonance with regards to NMR spectroscopy. The amount of energy required for each proton to spin flip tells us about its electronic environment and thus the structure of the compound. NMR requires a strong magnetic field and radio wave energy. The strength of the magnetic field affects that energy gap. So different strength of magnetic fields will allow us to see different energy gaps. It correlates with the resolution. So for this, in terms of the instrument needed, you will need a very strong magnet. Usually superconducting magnets are used to acquire magnetic fields such as 7 Tesla or even higher. A strong magnetic field is created when a high current is passed through a superconducting material at extremely low temperature. These are type 1 superconductors, about 4 Kelvin. This is very, very low temperature, usually the temperature of liquid helium. The greater the current, the greater the magnetic field. So as you can imagine, working at so low temperatures is actually quite expensive. So NMR, in terms of practicality, is quite an expensive technique, especially if you want high resolution. So another sort of subdivision is the post-Fourier transform spectrometers. In this case, a brief pulse of radio energy is used to excite the sample. Each of the atoms is excited and then relaxes, emitting energy, right, as part of that relaxation process. And that emitted energy is then recorded as what we call free induction decay, when you decay from an excited state down to a relaxed state or ground state. So that's the FID. The FID contains all of the information for each of the atoms, so it's just a matter of interpretation of that FID. A mathematical treatment, we call that a Fourier transform. It separates the signals so an individual signal can be observed for each atom that was excited. Often, multiple FIDs are taken and averaged together. This is to maximize resolution, maximize that signal to noise ratio, etc. Before the analysis, NMR samples have to be prepared neat or in a liquid solution, usually a deuterated solvent. Deuterium is an isotope of hydrogen, and we use it because it has an even number, right? So instead of the odd that you will see in hydrogen, it's actually 2. And placed in a small NMR tube. The sample is placed into the magnetic field, and the tube is spun at a high rate to average magnetic field variations or tube imperfections. This is what your typical NMR is going to look like. You have the instrument here, all your superconducting magnets. It's actually pretty large. I'm not sure the image does justice to it. This is like 6-7 feet tall. And the signals go here to the computer. This is what you analyze. This is what you put in the sample right here in the center. An example of a deuterated solvent will be chloroform D. So as you can see, no hydrogens, no protons. The sample is generally at room temperature when collecting the proton NMR spectrum. So the sample doesn't have to be at super low temperatures, it's just the magnets. NMR spectra contain a lot of structural information. This is a typical NMR spectrum right here. On the x-axis, you're going to see it says chemical shift in parts per million, and then some form of intensity here. So out of this, you're going to look for 4 things. 1, number of signals. then the signal location where they appear, call that the chemical shift, the intensity, that's the area under the signal, and the signal shape, we call that the splitting pattern. We'll talk about that as we move through the chapter. Let's start with the number of signals. The number of signals in a proton NMR spectrum indicates the number of different kinds of protons in a compound. Identical protons are chemically equivalent. Such protons fall into the category of being either homotopic or enantiotopic. Homotopic protons happen if the molecule has an axis of rotational symmetry that allows one proton to be rotated into the other without changing the molecule. So they're sort of equivalent or indistinguishable, right? And when that happens, then we say that we have homotopic protons. We have a couple of examples here. This can actually rotate, and we won't be able to tell them apart. The same is true for the 3 protons here and here, so on. Another test for homotopic protons is to replace the protons one at a time with another atom. If the resulting compounds are identical, then the protons that you replaced are homotopic. Sort of like this right here. If I replace one hydrogen for a bromine, I'll either have this, or if I flip it, then I have this. These are not different molecules, they're exactly the same compound. I literally just flip this right upside down and I get this one right here. Now, enantiotopic protons are a little bit different. They happen if the molecule has a plane of reflection that makes one proton the mirror image of the other. So for example here, if I cut this molecule, or if I put a mirror on the plane of the slide, right, then this one will be reflected here, and vice versa. Same is true for these two. And here, this will be my plane. This one will be reflected over here. So these are all examples of enantiotopic protons. The replacement test is universal, so we apply the same test that we saw for homotopic protons. It'll work to identify any equivalent protons, whether they are homotopic or enantiotopic. If the resulting compounds, in this case, instead of being the same, they're enantiomers, then the protons that you replace are enantiotopic. Now, if when you perform the replacement test, you happen to produce diastereomers instead of enantiomers, then you can say that the protons you have are diastereotopic instead of enantiotropic, and they are not chemically equivalent. The protons are neither homotopic nor enantiotropic, then they are not chemically equivalent. They're different from each other, chemically speaking. Consider the 2 protons below here in 2-butanol. These protons cannot be interchanged by rotational symmetry or reflectional symmetry. In other words, if I try to rotate this molecule, then I'm not going to have necessarily the mirror image of it, right? So that means that they don't fall under neither homotopic nor enantiotopic. There are some shortcuts that you can take to identify how many signals you should see in the proton NMR. The more we practice this type of exercise, identifying and working with molecules and proton NMR, the easier this is going to be and the more intuitive. So let's look at this example here. The 2 protons on a CH2 group will be equivalent if there are no chiral centers in the molecule. Now, the 2 protons on that same CH2 group will not be equivalent if there is a chiral center in the molecule. So here, we actually have a chiral center right here. So what that means is that while these 2 protons are definitely equivalent, these 2 are not. One of the reasons you can actually rationalize this is that if you look at this proton, you look at what's next, then you look at what's next, and you look at what's next. Is it exactly the same as what you would expect on the other side, right? The environment sort of changes a little bit. That will generate a little bit of difference in that environment that each proton is going to be experiencing. The 3 protons on any methyl group will always be equivalent to each other. Multiple protons are equivalent if they can be interchanged through either rotation or a mirror plane. So in this case, if you look at this plane right here, this side is actually equivalent to this side right here. You see this methyl group, and then the protons, 2 protons. So the red ones are equivalent to each other, the blue ones are also equivalent to each other. These 2 should generate just the 1 signal, and then these 4, or actually those 6 on top, these 2 should This force should definitely be generating another signal. Recall that cyclohexane shares have 6 equatorial and 6 axial protons. The axial and equatorial protons have different electronic environments, right? They're different in energy, therefore those magnetic fields are also going to be different. Technically, there are 2 types of protons here, but only one signal is observed in the proton NMR in this case. At room temperature, the shear interconversion happens pretty fast. So you get a lot of conversions per second at room temperature. And the phenomenon of NMR, keep in mind that you have to align all of your electrons, right, either in favor or against that magnetic field, and then flip your betas to alphas, and that takes time. The NMR is just not fast enough to see individual structures, so it's going to average all of this out. The consequence, you get just one signal. If the temperature is reduced to minus 100 degrees Celsius or less, then that ring flipping is slow enough that you actually get to see those 2 signals. In many NMR solvents, about 1% of TMS, tetramethylsilane, is added as an internal standard. So it's going to be like our zero or our baseline. The frequency of the protons in TMS is lower than that observed for most organic compounds. The shift for a proton signal is calculated as a comparison to TMS, so that's our baseline. We call it the zero. So that delta of that chemical shift, we look at that observed shift in TMS and the operating frequency of the instrument, both in hertz. For benzene on a 300 megahertz instrument, that's going to be about this much, 7.27 times 10 to the minus 6. Because we're looking at these small numbers, that's actually how we get to the ppm. These two, they're hertz over hertz, so they cancel each other. You don't really have a unit. The hertz of the signal is different in different instruments, but the shift relative to TMS is constant. What that means is that those magnetic fields, right, when you're building your magnets, you're cooling them, even a slight difference in the temperature that you're using or a slight difference in the magnets will generate a slightly different signal. But if you're using the same baseline, so everybody's comparing to TMS, that means that all spectra should be the same. The shift relative to TMS, the delta that we saw here is a dimensionless number, so these 2 hertz are canceling each other because the hertz unit cancels out. Units for delta are often given as parts per million, which simply indicates that signals are reported as a fraction of the operating frequency of the spectrometer. Most proton signals appear between 0 and 10. That's going to be true for everybody except for carboxylic acids. They are going to show up 12 to 14 ppm or so. But everybody else, they should appear within that 0 to 10 ppm range. Early NMRs analyze samples at a constant energy over a range of magnetic fields. Low field strength, we call it downfield. High field strength, we call it upfield. So this is some of the nomenclature that we're going to see when we're analyzing our NMR spectra. Shielded protons require a stronger external magnetic field to be excited at the same energy as a de-shielded proton. Current NMR analyze samples at a constant field over a range of energies instead. We sort of flip the script now. Shielded protons have a smaller magnetic force acting on them, so they have a smaller energy gap and absorb lower energy radio waves. So we look at downfield, they're actually on this side, whereas upfield tend to happen on this side of the graph. So downfield, upfield. Alkane protons generally give signals around 1 to 2 ppm, so they're very upfield. Protons can be shifted downfield when nearby electronegative atoms cause de-shielding. So what that means is that when I only have carbon hydrogen, I should expect a very low chemical shift, so about 0.9. I added iodine, that's one of my halogens, it's highly electronegative. You know, it more than doubled, right? It went to 2.2 ppm. And as I keep moving, I look between hydrogen and fluorine. I went from 0.9 to 4.3 ppm. That's a very dramatic change just by changing one atom. And that's the effect of that electronegativity with regards to that interaction. The same is true for a molecule that has more than one carbon, like the one we see here. This is an alkyl halide. We see chlorine, highly electronegative. That alpha carbon is going to have a shift of 3.3 ppm. Is the one that is most affected by the electronegativity of chlorine. But as I keep moving away, that effect sort of goes away also. So you can see I went from 3.3 to 1.6 to 0.9 ppm. When the electrons in a pi system are subjected to an external magnetic field, they circulate and produce a magnetic field themselves. They cause what we call diamagnetic anisotropy. What that means is that different regions of localized space are going to have different magnetic strength. Regions outside the ring have increased magnetic field. That's pretty much what happens when you have a delocalized pi system. The result of diamagnetic anisotropy effect is similar to de-shielding for aromatic protons. More magnetic field means more energy required to spin flip the protons. A consequence of that is that even though you have those carbon hydrogens that you would expect in really upfield numbers, right, really low numbers, your aromatics are actually going to be showing up around the neighborhood of 7 ppm, so fairly downfield compared to your alkanes. It is necessary to be familiar with the ppm values of these common types of protons. So this is just like with infrared. You're going to have some common values, some associated with different functional groups, different scenarios. The more familiarized you are with these values, the easier your life is going to be in these couple of chapters. So my advice is get practicing, start working this out with these tables until you become familiar with about where to expect each group with regards to that scheme, right, between 0 and 10 ppm, etc. Carboxylic acids, as I mentioned before, they appear much higher than 10 ppm. They go to 12, 13, 14 ppm, etc. Predict chemical shifts. We start with the standard ppm for the type of proton, methyl, methylene, or methine, and we go from there. Using the table we have here, 15.2, to adjust the ppm depending on proximity to certain functional groups. So we can actually start from our base values and then we keep moving based on context. Context is super important, both here and on IR, because depending on whether you have a highly electronegative or not next to your carbon, then the interaction between that photons and that matter is going to be a little bit different. Now let's talk a little bit about integration. When we talk about integration, we're talking about the area under the peak, and it helps us quantify the relative number of protons giving rise to a specific signal. Remember when we talked about methyl groups, so CH3, they're all equivalent. All three of them contribute to one signal. That one signal that is a collaboration of 3 protons is going to be more intense than if it were just a 1 proton. So we're able to sort of quantify that to an extent through integration. Usually you can do this by hand, but today most NMRs, they have a computer that will calculate the area of each peak representing that area with what we call a step curve, like the images you see here. And then it'll give you integration values like the numbers you see here in red. Those values that you get from the computer, from the integration, you need to adjust them to whole numbers, right? Because you're dealing with whole number of protons. You can't have half an atom or a third of an atom. You have 1, 2, 3 atoms. So usually a ratio of these numbers, one to the other, works well. If the integration of the first peak is doubled, the computer will adjust the others according to the ratio. And based on the numbers we just saw, you can tell that this is a collaboration of 2 protons, 3 protons, etc. So as you can see, as you can imagine, this is actually pretty powerful for telling us not just what atom is next to the protons that are generating the signal, but how many protons are generating the signal as well. So these are 2 key pieces of information we're getting up to this point. The integrations are relative quantities rather than an absolute count of the number of protons. In other words, they're a ratio. So a 2 to 3 ratio, it could mean that you have 2 protons one side, 3 protons on the other. It can also mean that you have 4 and 6, right? You can have multiples of this 2 to 3 ratio. So it's important to take this as just one piece of information and then sort of correlate with everything else you have going on. Symmetry has an effect on integrations. It's actually a good example of that. This would actually be a 2 to 3, like the one I just mentioned. You have 2 protons here, 2 protons here, so that's 4, 3 and 3, that's 6. So you have a 4 to 6 or a 2 to 3 integration ratio. The molecular formula, we have one right here. It must be known to know the absolute ratio. In this case, actually 4 to 6, not 2 to 3. So what that means is that with that 2 to 3 ratio, unless you have additional information, you can't go beyond that number. So a mass spec, for example, will be very good to complement this information. Or just the molecular formula actually would be very, very useful. Now let's talk a little bit about multiplicity. This is what we call the splitting patterns. This is the number of peaks in a given signal. So we've seen signals that look, let's say, something like this, a sextet, for example. So sextet because it has 6 little peaks. This is not necessarily 6 signals, it's actually one signal that is split into 6 smaller peaks. No? So all of these represent one signal, and all of them have different environments. We're going to get into the details in just a second. So we have the singlet, that's just one, doublet, that's 2, triplet, 3, etc. So how does multiplicity happen? Multiplicity happens when you have a magnetic field and you have protons next to each other. Let's say in this case you have proton A, you have proton B. Proton A can align itself in favor of the magnetic field, and proton B can do the same, right? So you would have, let's say, spin up or alpha and then spin up, so that will be A and B. They can also both align themselves against the field, or you can have one in favor, one against, and then one in favor, one against. I'm just gonna draw it over here. I don't wanna mess up the molecule. So you have these combinations right here. You have 1, 2, 3, 4 combinations. By just having a proton as a neighbor, right? You want just one neighbor. So you have them right here, both against the field, both with the field, and then one with, one against. Now these two, you can't really tell them apart at all. But in all scenarios, right? Let's say you have all scenarios, 50% of the time, because you have 4 possible scenarios, then 2 out of 4, so 50% of the time is gonna be this guy right here, 25% of the time is gonna be this one, and 25% of the time is gonna be this one. So what do you get? You get 2 smaller peaks, one that is larger, and it has to do with the possibilities you have for that electron and for that proton alignment. Keep in mind that you don't have one molecule, you have billions upon billions upon billions of molecules. So when you have that, then all possibilities actually do happen with a frequency that's sort of similar to what you will see in classical statistics. So we call it triplets. Now in this case, let's look at a scenario where proton A is split by 3 different neighbors. So these 3. In that case, you actually have these 4 scenarios, and you get a peak that represents those 4 scenarios as well. And the table we're going to see next, that's 15.3. It will show you the multiplicity trend continues. And by analyzing the splitting pattern of a signal in the proton NMR, you can then determine the number of equivalent protons and adjacent carbons. So you can sort of do the same analysis we just did backwards, right? You know the number of peaks, and from there you can tell how many neighbors you're going to have. You had a quartet, you had 4 peaks, that means that you had 3 neighbors. So it's going to be 1 less than the number of peaks that you have. Here's the multiplicity, relative intensities, from singlet all the way to septet. Now for splitting, let's look at these 3 key rules. Equivalent protons cannot split one another because they resonate together. To split each other, protons must be within 2 or 3 bond distance. So if you have a really long chain, let's say octanol for example, 8 carbon atoms, carbon number 8 is not going to have an effect on carbon number 1. It has to be near each other. Under typical conditions, splitting is observed only for protons attached to carbon atoms. Protons on oxygen or nitrogen generally do not couple with neighboring protons. That's because of the difference in electronegativity. The degree to which a neighboring proton will couple to its neighbor is called a coupling constant, and we assign to it what we call a J value. The J value is the distance between peaks of a splitting pattern measured in units of hertz. Basically how far apart those little peaks are. Protons splitting each other will have the same coupling constant. So if A splitting B, then B splitting A with the same intensity is basically what that means. Higher field strength instruments will give better resolution between peaks because the coupling constant is a smaller percentage of the overall hertz available. 300 MHz spectrometer avoids overlapping of peaks compared to the 60 MHz spectrometer. In other words, the stronger the instrument, the better it is at resolution, resolving these different peaks. This is a lot easier to read than this right here, even though they're both analyzing the same compound. It comes down to the resolution and the quality of that instrument. Really good instruments that allow you to analyze biomolecules go all the way up to gigahertz. Those are multi-million-dollar instruments, so you don't expect to see them in many institutions. Sometimes recognizable splitting patterns will stand out in a spectrum. An isolated ethyl group gives a triplet and a quartet. The triplet and quartet must have the same coupling constant if they are splitting each other. In other words, the distances are going to be the same here as they are here. Peak with an integration equal to 9 suggests the presence of a terbutyl group. So these are some generalizations, some trends that you're going to see. The more you practice, the more you see that this actually holds really well and allow you to sort of work through this a little bit easier. An isolated isopropyl group gives a doublet and a septet, just like the one we see right here. Splitting is not something that we observed in every single proton there is. Let's look at ethanol, for example. Ethanol will expect 3 signals, one for the CH3, one for the CH2, one for the OH. The protons bonding to carbon split each other, just like we would expect, but the hydroxyl group is not split. So that's this one right here. The hydroxyl group and other labile or exchangeable protons undergo what we call rapid exchange with trace amounts of acid. Such exchange blurs the shielding de-shielding effect of the neighboring protons, giving a singlet that is often broadened. So that's the expectation with those OH groups. The 3 molecules below might be difficult to distinguish by IR or by MS. Especially IR, you have, and MS really, you have the same molar mass. With IR, you have the same functional groups, but with NMR, you have easily distinguishable signals, right? You have these AH3s, they are very symmetrical. So you would see one signal here, another here, 3 signals. In this case, this signal is going to be different than this one. So you have 1, 2, 3, 4 signals. And then here, these 4 protons are actually similar. So you should expect just the 1 signal and then a second signal here. So these are all things we can do with NMR. That's why it's so important that we familiarize ourselves with it. That's why organic chemists really like it, because it's actually much more powerful than infrared or MS. With a given formula and proton NMR spectrum, you can determine a molecule structure in a 5-step process. We have the steps right here. The first step is going to be the degrees of unsaturation. We actually saw that with our MS, or hydrogen deficiency. Consider the number of NMR signals and their integration. We analyze each signal and we start drawing fragments consistent with each signal. So we look at each signal individually and then we put it together. We assemble the fragments into a complete structure. Lastly, we verify the proposed structure that it is consistent with all effect spectral data. Typically, NMR by itself is enough for us to identify a molecule, although we usually use it in conjunction with IR, so that it allows us to one technique corroborates the information from the other. It's a really good way to have a very reliable conclusion. Now, let's talk a little bit about the carbon NMR spectrum. Because proton NMR is by far the most abundant isotope of hydrogen, then proton NMR signals are really strong. Carbon-13, on the other hand, that's not the most stable or abundant isotope. It's actually carbon-12. Carbon-13 only accounts for about 1% of carbon atoms in nature. So a sensitive receiver coil and or concentrated NMR sample is needed. In proton NMR, shift, splitting, and integration are important. In carbon NMR, because you have so few of these carbon atoms, just 1% approximately, only the number of signals and the chemical shift will be considered. That's the only thing you really can consider. In carbon NMR, the proton-carbon splitting is often so complex that the spectrum is unreadable. To elucidate the carbon spectrum and make it easier to determine the total number of carbon signals, carbon NMR are generally decoupled. What that means is that we sort of remove the signals generated from proton NMR from the carbon NMR signals. So we sort of separate them and just look at the carbon signals. In the vast majority of carbon-13 spectra, all of the signals are singlets. Compared to proton, carbon-13 atoms require a different frequency of energy to excite or to enter in that resonance that we had talked about earlier. Compared to the standard TMS, carbon NMR signals generally appear between 0 and 220 ppm. This is actually a very important distinction because now if you're given an NMR sample, doesn't really matter if it's proton or carbon, you should be able to tell them apart. Proton NMR goes from 0 to 10 approximately. Carbon NMR goes from 0 to 220. Very large difference. Each signal in a carbon-13 NMR spectrum represents a unique type of carbon. Planes and excess of symmetry can cause carbon atoms to be electronically equivalent. Here, for example, we have a few scenarios where symmetry has an effect on the number of carbon-13 signals. So these two, if you look at the plane of symmetry here, these two are equivalent, so that's one signal, two signals, 3 and 4. In this case, it's a little bit different. These two are similar, so you get one signal. B is by itself, so it's E, so that's two different separate signals, so that will be 3, 4, and 5. And then here, if you look at that 1, 4 position, these two carbon are equivalent, so are these two, and then these 4 are also equivalent with each other. That will be 3 signals, different intensities though. Just like with proton signals, chemical shifts for carbon-13 signals are affected by shielding or by deshielding. So you get stuff that is more downfield, stuff that is more upfield, and functional groups or atoms attached to carbon that will sort of fall under very specific ranges. Carbon-13 spectra generally give singlets that do not provide information about the number of hydrogen atoms attached to each carbon. For that reason, specifically, proton NMR is usually preferred over carbon NMR. So distortionless enhancement by polarization transfer, or DEPT, carbon NMR, this is a technique that provides information about the number of hydrogen atoms attached to each carbon. So DEPT 90, only CH signals appear, but if you use DEPT 135, then you get CH3 and CH2. Signals all across the entire spectrum. The PT90 only CH, just like we just saw. So you get, and this is very interesting because in 135 you actually get positive and negative signals. So they go up or they go down depending on the type of carbon-hydrogen bond that you have. This is in a super common technique. It's not often used because typically you just use proton, and the same instrument usually does carbon as well, so you can have both of them separately and you get the same information you would with one of these. Lastly, one of the applications we have for NMR, that NMR phenomena, is with MRI, magnetic resonance imaging. These are essentially proton NMR spectrometers. The body is analyzed rather than a sample in an NMR tube. Different tissues have different concentrations of protons, so we sort of analyze the whole thing. And the advantage is that the energy we use for NMR is really low energy, so you don't really expose the patient to any type of high energy, so no side effects are experienced from an MRI. That's a big advantage.